Back to page 3 of Applications of Calculus and Kinematics. Number 3, when a ball is thrown, its height above the ground is given by S of t equals this equation, meters, where t is the time in seconds. Of course, at time equals 0, that's exactly when the ball is thrown. A, from what distance above the ground was the ball released? So, isn't that right when it's thrown? So aren't they asking what is S of 0? So if I put 0 in for t and t, you can see that the last two terms become 0. I don't even need the calculator to tell me that. At S of 0, the height is 1.2. Find S dash of t and state what it represents. Okay, so S dash of t, of course, is the derivative of this S function. If I find the derivative, the 1.2 becomes 0, 28.1t becomes 28.1, and negative 4.9 t squared becomes negative 4.9. The coefficient just stays there. The 2 comes down. The t has an exponent now of 2 minus 1 equals 1, which is equal, simplified to 28.1 minus 9.8t. What does it represent? S dash, the derivative of the displacement, is a velocity function. C, find t when S dash of t equals 0, and what is the significance of this result? Okay, so let's look at C. So t when S dash of t equals 0, so let's write S dash of t down here. Remember, it's 28.1 minus 9.8t. What we want to do is we want to solve for t so that the left side equals 0. We can do that with some easy algebra. We can subtract negative 28.1 from both sides, and then we'll have negative 28.1 on the left side, and we'll have negative 9.8t on the right side. 28.1, 28.1 divided by 9.8, it's about 3. 2.88. So t equals 2.88 is the answer to part C. What is the significance of this result? So remember, velocity equals 0 is when something is stopped. When you're throwing a ball, it might be when it changes direction from going up to going down. So I would say it is the moment when changing direction from going up to going down. Okay? So that would be when it reaches its maximum height, okay? Oh, by the way, in part D, they say, what is the maximum height reached by the ball? We can figure that out by finding out when the derivative, S dash, is equal to 0, right? We can find maximum minimums by setting the derivative equal to 0. Oh, wait a second. We already did that in part C. So it turns out that the time when the maximum height is reached by the ball is t equals 2.88. They want to know what is the maximum height reached by the ball. We can take that 2.88 and we can plug it back into the original S of t function. So we can do that by, I think the easiest way to do that, especially when we have so many other questions that they're going to ask, which probably are going to refer to it again, we can go ahead and type this function 1.2 plus 28.1 t, which we'll put x instead of t, minus 4.9 t squared. And then we're going to look at the table. And then they want to know what is the height at, they want to know what is the height at S of 2.88. Let me show you a trick to do that. One is you can look at the graph, and then we could do trace 2.88. So we'll do that first. Trace 2.88. Enter, and the answer is 41.5. Okay, another way you could do it is you could go to second table and you could set the step size to 2.88. So you put the cursor on 0 and then you set the delta table to 2.88, and then the second row is going to have the t equals 2.88 value, which is also 41.5. Okay, so that was part C, and part D, maximum height reached by the ball, 41.5. Find the ball's speed when released at t equals 2, at t equals 5, etc. I'm just going to fix the table set back to 1. Okay, and all right, oops, oh, I messed it up. Second table set. Put table start to 0, and now it's going to be fine. Okay, now we want to find the ball's speed when released at t equals 2 and t equals 5. So blue function is s. Let's find the derivative function, or let's put in the derivative function into the red function. Let's see, that would be velocity is 28.1 minus 9.8 t. So I'm going to put 28.1 minus 9.8 t, which is 9.8 x table. Okay, now they want to know the ball speed when released, so that would be 28.1. They want to know it at 2 seconds, that would be 8.5. And they want to know it at 5 seconds, that would be negative 20.9. Okay. State the significance of the sign of derivative of s dash of t. So remember, velocity positive negative means it's going to the right or going to the left. In this case, it's height, so it's going up. So s dash greater than 0 means it's going up. And s dash less than 0 means it's going down. Okay, how long will it take for the ball to hit the ground? The ball will hit the ground when it reaches 0 for the second, or for the first time, I guess, because it starts out at 1.2. It doesn't start at 0. So it goes up, and then do you see how between t equals 5 and t equals 6 it apparently hits 0 because the s function becomes 0 between 19.2 and negative 6.6 at some point. How can we find that point? Well, one of the ways is we could set, let's see, f. One of the ways we could do it is we could set s of t equal to 0, and we could solve for that, okay? Since we already have it in the calculator, I'm just going to graph the blue function. So I'll turn off the red function so it doesn't confuse us, and then I'm going to graph the blue function. It's going to be a parabola. The ball is going to go up and it's going to go down. Maybe we can change the window so that it goes up to y max of maybe like 50 or something. That should be plenty high. And then we can see when the ball hits the ground again. It's right there, okay, between 5 and 6, right? So how do we find that? We could do second calc 0 to find the x-intercept. So second calc 0. And if you were to do this by hand, of course, you would do it by doing quadratic formula, because basically what we're doing is we're setting a parabola equal to 0. Yes. Okay, so it's 5.78. 5.78. So t equals 5.78 is when it hits the ground. All right. And finally, G. What is the significance of s double dash of t? So s double dash of t is the second derivative, and if I took the second derivative, if I took the derivative of the velocity, which is the first derivative, 28.1, the derivative is 0, and negative 9.8 t, the derivative is negative 9.8. So this is actually the acceleration also. So the acceleration is negative 9.8 meters per second squared. For those of you in physics, this is a familiar acceleration. It's the acceleration of gravity near the surface of the Earth. So what was that again? So G, what is the significance of f double dash t? It's the acceleration of gravity. Okay, it's the acceleration for this displacement function. All right, I think that's it for this one. Let's move on to the next one. Number 5, a particle moves in a straight line with displacement function blah 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 centimeters where t is in seconds. Find velocity and acceleration functions for the particle's motion. Okay, so for part A, all we're going to do is we're going to find velocity and acceleration. Remember, we have the displacement function. How do we find velocity and acceleration? We take the first and the second derivative. The first derivative of s dash of t is equal to 12 because the derivative of 12t is 12. The derivative of negative 2t cubed would be negative 2. We just leave the coefficient there. We bring down the 3. We reduce the 3 by 1. And then the minus 1, the derivative is 0. So we simplify and we get 12 minus 6t squared for the velocity. For the acceleration, we're going to take the derivative of 12, which is 0, and then we're going to take the derivative of negative 6t squared, which is going to be negative 6 times 2t to the first, which is negative 12t. So our acceleration in this case is negative 12t. And that is part A. Let's do part B. Part B says, find the initial conditions and interpret their meaning. So the initial conditions are what is going on with s, v, and a at t equals 0. So let's find out. S of 0, what's going on? It would be 0 plus 0 minus 1. So it would be negative 1. So the displacement at s of 0 is negative 1. Okay, maybe that could be interpreted as 1 centimeter to the left of the origin. What is the velocity doing? So the velocity is equal to the s dash of 0, which would be 12 minus 0. So it would be 12. So that would be a positive 12, meaning it's moving to the right at 12 centimeters per second. And finally, acceleration 0 would be s double dash of 0, which is equal to negative 12t, and if t is 0, that means that the acceleration is 0 at that moment. So the initial conditions are the displacement is negative 1, the velocity is positive 12, and the acceleration is 0. Those are the initial conditions. It means that acceleration of 0 means it's moving at a constant velocity or constant speed, plus 12 means it's moving to the right at 12, and at that moment it is in position negative 1. All right? That's how we interpret the initial conditions. C, find the times and positions when the particle reverses direction. The particle reverses direction when the velocity equals 0. The velocity is equal to 0 when the first derivative is equal to 0. So we need to find out when the first derivative is equal to 0. What's the first derivative function again? It's this one, 12 minus 6t squared. This is a pretty easy equation. We don't really need the calculator to solve this one. We can subtract or add 6t squared to both sides, and we get 6t squared equals 12. We could divide 6 by both sides. We'll get t squared equals 2. And so t is equal to plus or minus the square root of 2. Of course, we are using only the positive part of t, so we don't need negative square root of 2. We just need positive square root of 2. So at this moment, t equals positive square root of 2 is when the velocity is 0 and it is changing direction. The other thing it asks us at this moment is the position where the particle reverses direction. We know that the time it reverses direction is positive square root of 2. Let's use the s function, which is s of t, to find out what position it is at when it changes direction at t equals square root of 2. We're going to plug square root of 2 in for all the occurrences of t. And we get this very messy function. This gives us 12 square root of 2 minus, let's see, 2 times square root of 3 minus 1. So let's see, that would be 12 square root of 2 minus 4 square root of 2. That would be 8 square root of 2 minus 1. Okay, so the position it's at when it reverses direction is 8 square root of 2 minus 1. Let's find out what decimal value that is approximately. So 8 square root of 2 minus 1 is equal to what? About 10.3. Okay, so about 10.3 is the position that it reverses direction. Part D, at what time is the particle's speed increasing and velocity increasing? This is kind of hard to answer. basically when the velocity and the acceleration are working together in the same direction, that's when the thing goes faster. But remember, speed and velocity are physics terms. Speed means when is it going faster, and velocity not necessarily, because velocity increasing could mean a positive number becoming more positive or a negative number becoming more positive. And if it's a negative velocity, meaning it's going to the left, if it's getting more positive, then that means it's kind of slowing down, right? The speed is actually decreasing, but the velocity is increasing. So it's I think it's going to help to make us a motion diagram to show what's happening here. So we're going to make a motion diagram. The motion diagram uses on its number line the values of the displacement. So where does it start? Remember, it starts at -1. So our starting point is s equals -1. And at that moment, it is going to the right at speed 12. So it's going to go to the right. Okay. It immediately is going to start slowing down because look, the acceleration is -12t, and remember, t is always a positive number in our experiment. So basically, at the moment it starts, the acceleration might be 0 because t equals 0, but right after that, t is positive, so the acceleration is going to be constantly blowing against the particle's motion here. And eventually the particle turns around at t equals square root of 2, right? So at t equals 0, it starts off at -1, but at t equals square root of 2, the particle turns around, and it turns around at the position 10.3. And then once it turns around, notice that the acceleration is blowing it hard to the left, so it's going to speed up as it goes to the left. Okay, so the first question is, when is the speed increasing? The speed is increasing when the velocity and the acceleration are going in the same direction. So after t is greater, when t is greater than the square root of 2, the thing starts blowing hard to the left, right? And the speed is increasing, right? What about when is the velocity increasing? So this is a little difficult. Okay, so the velocity is positive when it's going to the right here, right? The velocity is positive. But the acceleration is making it go slower to the right, so it is not, the velocity is not increasing here, right? And then it turns around, and then the velocity, which is at this point negative because it's going to the left, is getting increasingly negative because the acceleration is making it go faster. Okay, but a negative velocity becoming more negative is not increasing, right? The quantity is decreasing. It's getting more negative. So when is the velocity increasing in this scenario? Never. Okay, when it's going to the right, it's slowing down. Okay, it's a positive number getting less positive. Okay, so decreasing. When it turns around, it is a negative number becoming more negative. So it is also technically decreasing. So the velocity is never increasing. All right? That's it for this page.